We talked about potential difference in current, but how are they related? The Ohm's law, which is probably one of the most fundamental laws of electricity, explains this relationship. George Simon Ohm, after whom this law is named, was a German physicist of the early 19th century who spent many years researching on the factors that affect current flow in a battery. He found that the current in a steady-state conductor is proportional to the voltage between the ends of the conductor. So if V is the potential difference of this conductor from point A to point B, and a current I flows through it, I is proportional to V. What Ohm also discovered was that current is inversely proportional to the resistance offered by a conductor. What is resistance? Imagine a river flowing downstream from a mountain. The river will encounter several rocks and boulders which will block its flow. In other words, the rocks act as a resistance to the flow of the river. Similarly, conductors also offer resistance to the flow of current. So if R is the resistance of the conductor, I is inversely proportional to R. Combining these two terms, we get I is equal to VR or V is equal to IR. The reason why we represent Ohm's law as V is equal to IR is because it's a lot easier to print in textbooks and reading material. Let's dwell on this resistance a bit more. There are two kinds of resistances offered by a conductor. The first type is to do with the material of the conductor. As the free electrons travel through the conductor, they also experience a force from the positively charged nucleus of the conductor atoms. This force of attraction resists the flow of current. The attraction force is more in certain conductive materials and less in other, depending on the type of atoms they're composed of. The size and shape of the conductors also affects the resistance they offer to current flow. Instead of having a conductor of length L, let's take a conductor with double the length 2L. This now means that the electrons will have to travel double the distance as before. Double the distance means double the number of positively charged atoms to deal with along the way, hence in effect doubling the resistance offered by the conductor as a whole. The cross-sectional area also affects the resistance. Imagine 25 cars at a signal, all moving through a two-lane, one-way street. The traffic can move pretty fast now as there's lots of space for the cars to move. But what would happen if those same 25 cars had to go through a one-lane street instead? The traffic won't move freely anymore as we have only one lane instead of two lanes. Similarly, when we cut the cross-sectional area of the conductor by half, we are in effect reducing the movement space of the electrons by half and doubling the resistance. So if we sum all this up, R is proportional to the resistivity of the conductor material, which is denoted as ρ. R is proportional to length, and inversely proportional to the cross-sectional area, as decreasing the cross-sectional increases the resistance. Hence R is equal to ρ times L divided by A. R is quantified in ohms, named after the person who discovered it. So our V is equal to IR relationship can now be rewritten as V is equal to I times ρ times L divided by A. We now know the relationship between voltage, current, and resistance. But how is the electric field, which triggers this whole charge flow process, related to the current? We can use the same V is equal to I ρ L divided by A formula to calculate the relationship between the electric field and the current density. Current density is nothing but the current per unit area flowing through the object. So let's say I have this conductor of length L placed under an electric field E. So how would my voltage and electric field be related? Simply put, the electric field is the force on the unit charge of the conductor. We've discussed electric potential before. The electric potential of voltage between the two ends of the conductor is a measure of the work done on the unit charge to move it from point X to point Y. Work is nothing but force times distance, so if we multiply the force per unit charge by the distance between the two ends of the conductor, we have our conductor voltage. Therefore, Vxy is equal to E times L. The current density or current per unit area is denoted by J. So if I have a current I passing through a conductor of area A, I is equal to A times J, or J is equal to I divided by A. So if I now take my V is equal to I rho L by A formula and substitute the first V is equal to EL relationship on the left hand side of the equation, and also replace the I by A on the right hand side by J, the equation now becomes E times L is equal to rho Lj. If I cancel out the L on both sides, we get E is equal to J rho. Since both electric field and current have a direction of flow associated with them, we can represent this relationship using vectors. If you look at it conventionally, the direction of an electric current is the direction in which the positive charges or the protons flow under an electric field. The way we think of it in a circuit is that if a positive charge moves in one direction, say from A to B, then the electrons or the negative charges move in the opposite direction, from B to A. Now, when you hear this for the first time, this convention might not make much sense to you, as we've discussed all along that it's the electrons that are responsible for the current flow. The positive charges are tightly bound to the nucleus of the atom and hence don't move. But as all conventions go, this one is a little bit old and outdated as well. This theory was set up at a time when the concept of atoms were unknown. Benjamin Franklin, who set this convention, thought that current flow was some sort of fluid that flowed from a positive higher pressure area to a lower negative area. Even today, all circuits are designed keeping this idea in mind. One thing you need to realize is that electric current is not always caused by the flow of electrons. In certain cases, such as silicon diodes, which are in every computer machine you have, the atoms of the conductor with the extra protons, we call them the holes, flow through the circuit, creating a current flow. So if I want to represent J in terms of E, instead of E in terms of J, we just bring this rho to the other side and get this. This sigma term here is the opposite of resistivity. We call it the conductivity of the conductor.